When most of us think about the most dangerous, unforgiving frontier, we think of space.
Right. Rockets, the vacuum, radiation.
Exactly, the cold, dark void. But what if we told you that the deepest parts of our own planet are, in fact, far more deadly?
And not just a little deadlier. We're talking exponentially harder to reach. And, believe it or not, less explored than the surface of the moon.
It sounds completely backwards, doesn't it?
It's the ultimate counterintuitive idea. I mean, we live on a water planet. But the physics of deep ocean exploration, it's so challenging that we actually have better, more detailed maps of Mars than we do for huge parts of our own ocean floor.
So the problem isn't really the distance.
No, not at all. It all boils down to one single terrifying concept: pressure.
And that is exactly what we're getting into today. Our mission for this deep dive is to understand why that pressure, the sheer weight of all that water, makes exploring the deep sea so much more difficult and dangerous than traveling to space.
And what that tells us about engineering, biology, and, well, our own planet.
Okay, let's unpack this. We have to start with the scale of the ocean because that's what creates this incredible force.
To really get it, you have to internalize the sheer volume of water we're talking about. The average depth of Earth's oceans is around 3,700 meters.
And that's just the average.
That's the baseline. It's this enormous volume, people call it inner space, and it's mostly, out of sight, out of mind.
And isn't most of the planet's actual living space by volume in that deep, dark zone?
It is, yeah. Which makes it even crazier that we know so little about it.
Yeah.
But to really understand the physics, you have to look at the extremes.
So the Mariana Trench.
Mariana Trench, the deepest point on Earth, it plunges down almost 11,000 meters below the surface.
That's just a number, though. How deep is that really?
Okay, try this. If you took Mount Everest, the tallest mountain on Earth, and you placed it inside the deepest part of the trench, its peak would still be more than a mile underwater.
Wow. That is just breathtaking. You're talking about a column of water that's almost 7 miles high.
And that's what brings us directly to the crushing math of the water pressure.
Right. This is where the physics stops being an abstract idea and starts becoming a terrifying reality for engineers.
It's rapid, it's relentless, and it's completely unforgiving. The basic rule of thumb is that pressure increases by 1 atmosphere, or 1 atmosphere, for every 10 meters you go down.
Okay, so here on the surface, we're at 1 atmosphere. That's our comfort zone. That's what we're built for.
Exactly. Now let's say you descend. By the time you hit 1,000 meters, you're already at about 100 atmospheres.
100 times the pressure we feel right now.
And when you get all the way down to the bottom of the trench, 11,000 meters, that pressure is over 1,100 atmospheres.
1,100? Again, that's such a huge number, it's hard to really grasp. What does that feel like? I mean, what's a real-world equivalent?
The analogy that really hits home is this. It's the same as having more than 50 jumbo jets stacked on top of your body.
50.
All at once. Or, if you prefer, it's over 16,000 pounds per square inch. Your car tires may be 35 psi.
So we're talking about a force that, well, nothing from our world is designed to survive that.
Nothing. And what's fascinating here isn't just the final number, it's how quickly that force builds. There's just no room for gradual adaptation.
It seems like the first engineering problem before you even get in the water must be testing. Is it harder to simulate that kind of pressure on land than it is to simulate the vacuum of space?
That is a fantastic point. Yeah, space agencies, they have these huge vacuum chambers.
Right.
And while they're complex, a vacuum is just the absence of matter. It's zero pressure. But to simulate 1,100 atmospheres, you have to build a tank that can withstand that same force pushing out from the inside.
So the testing facility itself is under incredible stress.
It's immensely dangerous. It's a much higher risk environment than most space simulators, and that's a huge challenge before you even get near the ocean.
And that brings us to the core difference, really, between fighting the ocean and fighting space. That fundamental stress is completely opposite.
It is. When we send people or probes into space, the main problem is a lack of pressure. It's a vacuum.
Right. We need pressure to live.
So we build suits and stations that are pressurized. They push outward to keep everything stable inside. We're basically creating a little bubble of Earth to take with us.
So we're fighting against explosive decompression, pushing back against nothing. But, the air pressure here on Earth changes all the time. Why is a lack of pressure in space an easier problem to solve?
Because the physics are just, well, they're more forgiving. In the deep ocean, the problem is the complete opposite. It's too much pressure, and it's pushing inward from every single direction at once.
So the whole engineering approach has to flip.
It flips entirely. You're not trying to keep something in. You're trying to keep the entire ocean out.
And that's why engineers often say a deep diving submersible is, in some ways, a harder problem to solve than a spacecraft.
Exactly. The force of a vacuum is constant, right?
Mm.
But the ocean's force gets stronger with every single meter you go down. And the materials you need are totally different.
Lighter for space, I imagine?
Right. You can use composites, aluminum. But to resist that inward crush, you need incredibly dense, strong materials.
Yeah.
Specialized titanium alloys, ceramics.
And I remember reading that the shape of the vessel becomes absolutely critical.
It's everything. The most pressure-resistant shape there is a perfect sphere because it distributes all that external force perfectly evenly across the surface.
So there are no weak points.
No weak points. That's why deep diving submersibles, the ones that carry people, are almost always these small, thick spheres. You can't just build a big, roomy cylinder like the International Space Station.
Because a cylinder would just buckle under the pressure.
It has inherent weak spots. That geometry makes it much more likely to fail.
Which means your margin for error is basically zero.
It's non-existent. A spaceship might get a small puncture, a slow leak, that can give the crew minutes, maybe even hours to react.
But in the deep ocean,
One tiny flaw, a microfracture in the hull, a seal that isn't perfect, a bad weld, and that massive unrelenting pressure finds it. And the structure's overwhelmed, instantly.
and this is where we have to talk about what failure actually looks like, because
Yeah.
it's just pure, terrifying physics. A deep sea vessel doesn't spring a leak and slowly flood.
No, the structure implodes. It's a failure driven entirely by hydrostatic physics, and it happens with unparalleled speed.
The specifics here are just chilling. The crushing force moves inward faster than the speed of sound in water.
Which means the total collapse of the vehicle happens in milliseconds.
Milliseconds. That's literally faster than your nervous system can register a sensation.
It's faster than you can process pain. There is no warning. There's no escape.
And that must be a huge reason why deep-sea exploration gets less funding, less attention than space.
It's a profound reason. If a spacecraft fails, we often get telemetry data back, we find fragments, there's a timeline we can analyze.
You can figure out what went wrong.
Usually, yes.
Yeah.
But when a submersible fails that deep, the implosion obliterates everything. The vessel, the data recorders, any evidence. It's all gone in an instant. There's almost nothing left to learn from.
That lack of data just multiplies the risk, which leads right into what some people call the exploration paradox.
That's the disconnect, right? We've sent rovers driving for miles across Mars, we've walked on the moon, and yet something like 80% of our own ocean floor is still completely unexplored, unseen.
So why can we see hundreds of millions of miles away better than we can see 7 miles down? It's not the distance.
It's a distraction. The pressure actively demolishes the tools we need, and it makes every single part of the process slower and more expensive. Think about power.
Okay.
Deep-sea vehicles can't use normal engines. They need these expensive pressure-proof battery systems. And communication. Radio waves don't work well underwater.
So you're either stuck with a physical cable?
A tether, which is heavy, expensive, and a logistical nightmare under that kind of pressure. Or you have to use slow acoustic data transfer. It's like trying to download a movie over dial-up.
So the pressure doesn't just crush the walls, it dictates everything. The power, the speed, the comms making every single dive this slow, expensive, high-risk mission.
Precisely. That's why the gap exists.
Yeah.
The ocean literally hides its secrets behind the laws of physics, because the very things you need to explore, energy, structure, communication, are all being suppressed by the environment itself.
It's humbling, really. The forces right here on our home planet are what keep us from knowing it. And yet, despite all this brutal physics, there's life down there. Life that has somehow solved this problem.
It's truly miraculous that anything survives in that environment. I mean, perpetual darkness, near freezing temperatures, and that crushing force. But deep-sea creatures have evolved solutions that our engineering can't even touch.
We talked about how our vehicles need to be these perfect, dense spheres. How did these organisms do it? What's their trick?
Well, first, they can't have any air-filled spaces. No lungs, no swim bladders. Their bodies are mostly water and gelatinous tissue, which makes them basically incompressible.
So the pressure just passes right through them?
It passes through them instead of crushing them. They achieve pressure equalization by basically matching the environment.
So they don't fight the pressure?
They embrace it. That's the key. And beyond that, their biochemistry is it's phenomenal. They have these special molecules called piezolites.
Piezolites?
Yeah, they're pressure-stabilizing molecules. They protect all their essential proteins. Normal proteins, like the ones in our bodies, would just fall apart under that force. These piezolites keep them stable, so all the functions of life can just keep on going.
That is a feat of biological engineering that just puts our best materials to shame. They solved it with chemistry.
And if we connect this to the bigger picture, studying this life is so important. It's not just about cataloging weird fish. It's about understanding how high-pressure chemistry works.
Which could help us build better materials.
Better materials, breakthroughs in medicine, understanding how to keep complex molecules stable under stress.
And I guess it changes how we look for life elsewhere, too.
Absolutely. The fact that complex life is thriving at 1100 atmospheres, it gives astrobiologists real hope for finding life on icy moons like Europa or Enceladus.
Places with huge oceans under ice with similar crushing pressures.
Exactly. It proves that life finds a way, even when physics throws its absolute worst at it.
So we've kind of come full circle. We started with this premise that the deep ocean is deadlier than space. After all this, what does it all mean? What's the final lesson from the physics?
It means the danger comes from two opposite extremes. Space tries to kill you with emptiness, lack of pressure, cold, a problem we solve by pushing out.
Building a bubble.
But the ocean tries to crush you with overwhelming force, the sheer weight of the world pressing inward. And fighting that inward crush is just inherently harder, slower, and so much riskier than maintaining an outward push.
We can design and we can build, but at the end of the day, our own planet's gravity and water pressure set the limits far more strictly than the vacuum of space does.
The forces of physics really do remind us who's in control the deeper we go.
So the final thought for you to take away is this.
The deepest, most challenging mystery humanity has yet to fully unlock.
Yeah.
It isn't waiting for us up in the stars. It's pressing down on us from below.